Welcome to This Explainer. Today, we're embarking on a pretty amazing journey to demystify one of the most game-changing pieces of tech from the 21st century, the Arduino Uno. We're going to trace it all the way back to its super accessible origins at a design school in northern Italy, and then zoom right down into the microscopic timer interrupts pulsing away inside its silicon brain. So whether you're totally new to this and just trying to figure out what this little blue board even is, or you're an intermediate tinkerer ready to really master its hardware logic, well, you're definitely in the right place.
Okay, here is our roadmap for the explainer. 1. The birth of Arduino. 2. Anatomy of the board. 3. Inside the microcontroller. 4. How your code runs. And finally, 5. Mastering timer interrupts. We're essentially taking a zoom-in approach here, stepping down from the physical board itself right into the micrologic that actually runs your code. Let's get into it. Part 1. The birth of Arduino. Let's start by looking at the very specific educational problem this project was actually trying to solve back in 2003.
Picture this at the Interaction Design Institute Ivrea in Italy. Students who weren't engineers by trade were trying to build interactive digital projects. The big problem? They had to rely on a microcontroller system called the Basic Stamp, which cost anywhere between $50 and $100. For a student budget, that was a massive financial barrier. To fix this, Hernando Barragán created the wiring platform as his master's thesis, which simplified the programming and used a custom board. Then, in 2005, Massimo Bonzi and a team of developers forked that project to create Arduino, specifically to support an even cheaper microchip. Because they made it entirely open source, the hardware community just completely exploded, taking us to over 700,000 official boards in use by 2013, and literally millions more today.
And honestly, the naming story brilliantly illustrates its humble roots. The platform that literally sparked a global open-source hardware revolution was named after the Bardi Re Arduino. Yep, the local pub in Ivrea where the founders frequently hung out, which, funnily enough, was itself named after an Italian medieval king. Part 2. Anatomy of the board. Let's move from the history to the physical hardware and see what actually makes up this iconic blue board. When you look at the board, notice how the entire layout is essentially a complete support system for one specific component. That large 28-pin rectangular chip right there, that's the ATmega 328P. That is the actual brain of the operation. Everything else on this board is just there to help that brain function. You've got a 16 megahertz crystal oscillator acting as its heartbeat, a DC power jack and voltage regulators to keep it safely powered up, ICSP headers, and of course, a USB connection so it can communicate effortlessly with your computer. Surrounding that brain are the pins, which are how the Arduino actually interacts with the real world. The board exposes 14 digital pins, meaning they simply read or write on or off states. And as a really neat beginner feature, digital pin 13 is tied directly to a built-in LED right on the board, so you can test your very first code without any external wiring whatsoever. Now, 6 of those digital pins are marked with a little tilde symbol. These can use pulse width modulation to simulate an analog output by toggling on and off incredibly fast, which is absolutely perfect for dimming an LED or controlling the speed of a servo motor. Finally, you have 6 dedicated analog input pins routed to a 10-bit analog to digital converter. This basically maps continuous real-world voltages, think like a volume knob, into readable discrete digital steps from 0 all the way to 1023. We know what the pins do on the outside, right? But to truly master this hardware, we have to ask what the ATmega 328P is actually doing on the inside the second it gets power. Part 3. Inside the microcontroller. To answer that, we need to dig into the specific architecture hidden inside the silicon. I always like to visualize the internal layout of this chip, which uses something called a Harvard architecture, as a single-room office. The central processing unit is our worker, actively executing instructions one by one. The general-purpose registers, that's the desktop, holding files that are being actively modified right this very second. And because it's a Harvard architecture, our CPU worker can grab instructions from one place and write data to another at the exact same time. This optimizes throughput without creating any annoying bottlenecks. So, the really crucial point here is understanding the 3 distinct memory storage areas in this tiny office. First, your actual program code lives permanently in the 32 kilobyte flash memory, or fireproof filing cabinet. And yes, I said kilobytes. It's tiny, but it's incredibly efficient. Second, the active variables you create in your code are quickly shuffled around in the temporary 2 kilobyte SRAM, or the desk drawers. This is volatile, meaning it completely wipes clean when the power gets turned off. Finally, there's a tiny 1 kilobyte EEPROM, which acts like a combination safe. It's non-volatile memory that's just perfect for saving critical calibration settings that absolutely must survive a power loss. Part 4. How your code runs. Now that we know where the code actually lives in that flash memory filing cabinet, let's explore exactly how it gets there and how the microcontroller executes it. Let's see how this all builds from the very moment you apply power. Before your code even has a chance to run, a tiny, invisible program called the bootloader intercepts the startup sequence. It listens to the USB connection for about 1 to 2 seconds. If you just clicked Upload in your Arduino software, the bootloader enters write mode, receives your newly compiled hex file, and permanently burns it into the flash memory. But if it doesn't hear anything, it simply skips the programming sequence and jumps to a specific memory address, 0x0000, to hand control over to whatever sketch is already sitting on the board. The second the program counter hits that 0 address, your code takes over, and it's strictly divided into 2 mandatory functions. First up, this setup function. This executes exactly 1 time. This is where you configure the environment, like telling the board which pins are outputs or firing up a serial communication channel. Once setup finishes, control flows directly into the loop function. Just like the name implies, this block of code runs from top to bottom, and when it hits the end, it immediately snaps back to the beginning, repeating infinitely. This right here is where the core logic of your project lives, whether that's checking a button state or updating a display screen.
Part 5. Mastering timer interrupts. But what happens when the standard loop function isn't precise enough? Well, that brings us to our final, slightly more intermediate engineering concept.
Normally, the Arduino executes commands in the loop sequentially. If you use a delay command, the whole board basically just sits there waiting. But what if you need to read a sensor exactly every 1 second, no matter what else the code is busy doing? You use CTC mode, Clear Timer on Compare Match. This utilizes the hardware timers to momentarily pause your main loop, execute a separate set of instructions instantly, and then return you right back to exactly where you left off. Now, remember the Arduino's clock runs at 16 megahertz, that is 16 million ticks per second. Way too fast for human-scale timing. So we use something called a prescaler. This divides that clock speed down by factors like 8, 64, 256, or 1024, just to make the timing actually useful for us. By doing just a little bit of math, you can configure these interrupts perfectly. You take the 16 million hertz clock speed, divided by your chosen prescaler, multiplied by the exact frequency you want, and then just subtract 1. Boom! That resulting number is placed into the compare match register. The hardware timer will count up to that exact number, trigger your special code, reset to 0, and do it all again endlessly. The result? You get perfectly timed, professional-grade hardware execution, completely unaffected by whatever messy, delayed code you might have running in your main loop. Pretty incredible, right? From its origins in an Italian classroom to the deeply layered silicon architecture of the ATmega 328P, the Arduino Uno basically took hardware engineering and just completely demystified it for millions of people worldwide. It took super complex concepts like memory management, analog to digital conversion, and timer interrupts, and it made them accessible to anyone willing to learn. So, knowing how this incredible tool operates from the inside out, the only question left to ask yourself is, what are you going to build with it?